Travis, making sense?
Yeah.
For the moment, just so it didn't get too cluttered, I was leaving f like vague. But now it's not just f in general. There's a particular function that I care about, which is that one. So I just took. Is that one all right? Okay. What now? Garrett, what should we do now?
Well, you can just do it.
You can just do it. Yeah. He says just do it. So yeah, keep going. Just let's simplify all that crap in the brackets. So just like multiply all that out. Actually, it's not even that much, right? When you multiply it out, what do you get? It's like negative 4/25 I squared plus 5. Cool? Okay. And now, what seems like a good thing to do now? Oh, we did stuff like this actually back in pre-calc C, right? How do I sum up this expression? What's this mean?
Make it into 2 different sums.
Make it into 2 different sums, he says, yes. Let's split this up into 2 different sigmas and also factoring out like the stuff as we go, right? So this is going to be like negative 8 over 125 sum from I equals 1 to 5 of I squared. Does everyone see what I just did?
Yes.
Just the math. Jesus says good. You good? You good? Okay, and then what's left, Sandeep?
The plus 25.
Oh yeah.
Oh, and then
Wait.
2/5 of that.
Yeah.
Okay.
Yeah. Okay. Yeah. I was just going to actually do it in a. Yes, I think that is correct. But let's just keeping it simple. Let's just. This is really like the sum of a bunch of 5. So yeah, he's right. 25 times 2 which is 10. I'm just going to write it as. I'm going to pull the 5 out, and I'm just going to write it as 2 times the sum from I equals 1 to 5 of just like 1, which is really like the same thing. Someone see what I did? I'm splitting. I just inserted this step where I am literally splitting up the sigmas into 2 separate sigmas and pulling out all the coefficients to the outside. Okay. Oh man, if only I had a formula for the sum from I equals 1 to 5 of I squared. Do we have such formulas? We do. Yeah, they're all over here. So just like recall. Recall the sum from I equals 1 to n of. Well, I guess we can just do all these, right? Sum from I equals 1. The first one we did is the sum from I equals 1 to n of just I. What's that? n plus 1 over 2. If I just add up 1 n times, what do I get?
n plus 1 n plus. Is that one?
Wait, here, no, here. I got my student. Yeah, this is just 1 plus 1 plus 1 plus 1, and then we get n. And then we're like the hard ones, right? What's the sum from I equals 1 to n of I squared? That's the one I need right now.
n plus 1, n plus 2.
2n plus 1.
Oh, no.
Yeah, you were both saying the same thing, just at once.
Okay.
Cool?
No,
I think that's right. That's right, yeah.
I was
And
saying
then
plus 2. I knew
the
there was
last one, the sum from the last one that we did in class is the sum of the cubes of that.
It's the same as one of them. It's a lot.
Like
smaller.
that.
Sum of I
Yeah,
squared.
It's like, yeah, that's right. It's like this. It's the square of the sum of integers. And we looked at like cool reasons why that makes sense. Okay, so armed with all those formulas from last semester, I can just keep on going. So what is the sum of the squares? Like, just do it. Finish stuff. Apply the formula. I don't know, I didn't do it yet. It's like 10 times 1 plus 2 over 6. And then show. So I got that. What you got? Okay, count says good. So what is that? It's like 250 minus 88 over 25. That's like, what is that? 162? Come back me up there.
Yeah.
162 over 25. All right, and that is, I'll just write it in mixed number form, just like for fun. That's like 6. That's like 6 and 12, 26.
64.8.
No,
12
6 points. I think it's like 6. Yeah, 60 right. It's like 6.4. 12 25ths is 0.48. So yeah, 6.48. All right. I claim that the true area under this curve has got to be more than 6.48. Cool? Okay, so now we do it all over again. This time a little bit faster, but it's also a little bit harder. Alternatively, let's construct an upper estimate. We're gonna go over here.
Oh, it's over there.
So if we want an upper estimate, I'm also going to draw rectangles. But now, what should the rectangles look like? They should be like above. Yeah, picture for the 1,000 words. Draw some rectangles, do some shading, do beautiful things. Look at the person next to you. Let's do it.
Oh, are you doing like this or like above the curve or this? Yeah, are we doing like this or like, no, that doesn't make sense. Wait, how far above do you go there?
Did you guys do basically that?
Yes.
Yeah, so now, of course, I'm still using the curve, but if I want to construct an overestimate, then I want the rectangles to, and I'm using rectangles on 5 equal width subintervals from 0 to 2, then I want to draw my rectangles like that. Cool? Okay, and in fact, maybe now we should like do some, we should have some like, we should talk about what's actually going on a little bit. So there is a name for what we have been doing. This method over here is affectionately nicknamed RRAM. RRAM stands for right rectangular, right rectangular approximation method. It's like awesome. If we were in the army, we could have like hundreds of acronyms all the time, but we only have a couple. Why is it called right rectangular approximation method? Well, you said it's a method. It's an approximation method because we're approximating the area. It's a rectangular approximation method because we're using rectangles. And it is a right rectangular approximation method because the height of the rectangle is determined by the value of the function at the right-hand endpoint of the subinterval. I'll say that long calculus sentence one more time. It is called the right rectangular approximation method because we have drawn the rectangles in such a way that the height of the rectangle, this is called a subinterval. The whole thing is called an interval. These little guys are called subintervals. The height of the rectangle on each subinterval is determined by the value of the function at the right-hand endpoint of the subinterval. Follow? Sandeep, good? All right, Sandeep, what do you think this is called over here?
The left rectangular approximation.
Oh, he's so smart. Yes, this is LRAM. LRAM is the left rectangular approximation method. We're still approximating area using rectangles, but now for each subinterval, the height of the rectangle is determined by the value of the function at the left endpoint of the subinterval. Cool? Okay, and by the way, would somebody like to conjecture a sort of general theory about such methods and their overestimation and underestimation capabilities? Kendall.
Well, I mean, the actual is going to be in between them.
Oh, that's a thing to say, yeah. The true value is going to be somewhere in between, yeah, that's true. Some more.
I mean, depending on like the fire graph, the less it's going to overestimate or
Depending on the what of the graph?
like if it's flatter.
Yeah, depending on the flatness, probably like derivatives are related or something, right? Yeah, okay, she's depending on the flatness. Actually, if it's a total flat graph, then they'll both be just correct, because that's like, yeah. Yeah, you had your hand up.
Yeah, because all the rectangles in RAM are inside, it's going to be smaller, and because all the rectangles in LRAM are like outside. That's
Yeah, that always happens?
Well, if you're
Wait,
never mind,
concavity makes a
actually.
difference?
It depends if it's
Con-
increasing or
Does it
decreasing.
matter whether
Otherwise, it
it's-
would be the opposite.
Uses.
It depends on the concavity, because if it was
I heard you.
concave up, then
Um,
it would be the other way around, because if it's concave down, it's like this.
Comments?
Ethan said that first.
No,
I know, I heard it. All comments are, all things are being recorded in my infinite brain and cataloged by privacy. Good job, Ethan, except you're both wrong.
Yeah.
And
Yeah.
they're being cataloged here too.
Yeah.
Yo,
Like if you have f of x equals root x, like right, the RM would still, wait. That would underestimate.
you guys are supposed to figure this out now. Yeah, Kendall.
It's like decreasing and being concave up, then it's this way, and if it's increasing and being concave down, then it would also be like underestimated throughout the.
All right, look, there's a way to figure this out, right? I mean, just flip somewhere to some corner of your paper or whatever, and scribble or maybe notes if you're that kind of person, and draw 4 copies of the 4 different kinds of functions, which are concave up, increasing, concave down, decreasing. Yeah, you can. It's kind of where you can squeeze the remote.